Welcome to G Fun Facts Online. Today we are diving deep into a silent revolution happening at the very edge of physics, a place where abstract mathematics meets the messy reality of the quantum world to solve one of the oldest problems in engineering: noise. In the microscopic realm of nanosensing, noise is the ultimate enemy. For decades, scientists trying to detect single molecules or minute magnetic fields have battled against the chaotic fluctuations of the quantum world. Thermal vibrations, material defects, and random scattering all conspire to obscure faint signals. The traditional engineering approach was always brute force: build louder amplifiers or quieter, colder environments. But there is a new approach that takes a completely different path. Instead of fighting the chaos, it ignores it. This revolution is built on topological states of matter. This is a Nobel Prize-winning concept that has migrated from theory to experimental physics. We are talking about topological insulators, Weyl semimetals, and Majorana-based superconductors. These materials possess a secret code in their quantum wave functions that protects their electronic states from disruption. Imagine a sensor that is immune to the imperfections of its own manufacturing, or a detector that conducts electricity on its surface with zero resistance, regardless of scratches or impurities. This is the dawn of topological nanosensing. To understand why this is changing the game, we have to look under the hood at the physics of the unbreakable state. Unlike standard materials, where properties are defined by local atomic bonds, topological materials are defined by global mathematical properties. Let's start with topological insulators, or TIs. A TI is a material with a split personality. It is an electrical insulator in its interior, the bulk, but a highly conductive metal on its surface. The magic lies in something called spin-momentum locking. In these surface currents, an electron's spin is inextricably tied to its direction of motion. To scatter backwards, which is what causes resistance and noise, an electron would have to flip its spin. But in a topological insulator, this spin flip is forbidden by time reversal symmetry. For a sensor, this is revolutionary. It means the surface current is protected against backscattering. It creates a signal channel that is incredibly clean and robust, even if the sensor surface is rough or covered in biological molecules. Moving beyond insulators, we have Weyl semimetals, effectively 3D graphene. These materials host Weyl nodes, points in momentum space where conduction and valence bands touch. These nodes are connected on the surface by Fermi arcs, disjointed segments of electronic states that are topologically required to exist. The killer feature here is the chiral anomaly. When you apply parallel electric and magnetic fields to a Weyl semimetal, electrons are pumped from one Weyl node to another, violating classical conservation laws. This results in negative magnetoresistance, meaning the material actually becomes more conductive as the magnetic field increases. This property is being exploited for ultra-sensitive magnetic sensing that surpasses traditional Hall sensors. Then there are the ghost particles, Majorana fermions. Predicted in 1937, these are particles that are their own antiparticles. In superconductor semiconductor nanowires, they appear as Majorana zero modes at the wire ends. While they are the holy grail for topological quantum computing, their extreme sensitivity to the parity of the quantum state makes them intriguing candidates for sensors that detect minute changes in the quantum environment itself. But one of the most exciting recent developments for nanosensing is the non-Hermitian topological skin effect. In traditional physics, we assume systems preserve energy, but sensors are open systems. They gain and lose energy to the environment. When you combine topology with this open nature, something bizarre happens. Instead of just having robust edge states, all the bulk states of the material can collapse onto the boundary. This macroscopic accumulation of states creates an extreme sensitivity to boundary conditions. Researchers compare it to an ohmmeter, where a tiny perturbation at the boundary, like a single molecule binding, doesn't just shift a frequency slightly, but fundamentally alters the macroscopic current flow of the entire system. This offers exponential sensitivity that scales with the size of the system. The theoretical elegance of these materials is now hitting the road in tangible, high-performance applications. Let's look at biosensors. Topological materials are solving the trade-off between sensitivity and stability. Recent experiments have integrated Bi2Se3, a classic TI, with Prussian blue nanoparticles to create glucose sensors. The metallic surface states of the material facilitate rapid electron transfer, while the topological protection prevents signal degradation from the complex biological soup. These sensors have achieved detection limits in the micromolar range with exceptional stability. In another breakthrough, scientists coated bismuth 3-selenide with octadicylamine to create ordered templates for DNA assembly. The robust surface states improve the signal-to-noise ratio significantly, allowing for the detection of COVID-19 biomarkers with limits as low as 0.5 picomolar. There is also a concept called topological darkness in optical biosensing. These metamaterials are designed to have a singular point where they reflect zero light, creating perfect darkness. A binding event, like a virus attaching, destroys this perfect topological destructive interference, causing a sudden, sharp spike in reflection. This digital response of dark versus bright is far easier to detect than the subtle analog shifts of traditional sensors. In gas sensing, we are seeing devices for detecting hydrogen sulfide, a deadly industrial gas. New sensors combine a whale semi-metal layer with a 1D porous silicon photonic crystal. This setup excites TAM plasmon polaritons at the interface. Because the optical conductivity of the semi-metal is topologically linked to its whale nodes, it responds uniquely to the absorption of gas molecules, offering a sensitivity far surpassing standard dielectric sensors. We are even seeing this in acoustics. Sensing isn't just electrical, it is also mechanical. Researchers are building phononic crystals that mimic graphene to control sound waves. These structures host Valley Hall edge states, where sound waves propagate along domain walls without backscattering. These are being used to build ultrasonic sensors that can operate in fluids like blood without losing energy to scattering, enabling high-precision lab-on-a-chip devices immune to the viscosity of the sample. Of course, the transition from theory to device is paved with fabrication hurdles. Early topological devices relied on the Scotch tape method to peel off flakes of materials. That is not scalable. Molecular beam epitaxy, or MBE, is now the gold standard, allowing for atom-by-atom growth on silicon substrates. The holy grail is integrating these exotic materials with standard CMOS silicon chips. The challenge is the thermal budget, as many topological materials degrade at the high temperatures used in silicon processing. However, post-processing techniques and low-temperature transfers are showing promise. We are standing at the precipice of a new era. The biggest recent win is the observation of topological effects, like giant magnetoresistance at room temperature. This moves topological sensing out of the liquid helium cryostat and into practical devices. As we standardize the quality of these materials and develop topological transistors to amplify their signals, we are looking at a future where sensors are paradoxically more sensitive to their targets while being completely robust to their environments. From detecting a single strand of DNA to mapping magnetic fields with quantum precision, the topological revolution in nanosensing is just beginning. Thank you for listening to G Fun Facts Online.